Welcome back to another episode of the Natural Number Game in Lean 4. We're picking up right where we ended up last time and continuing the power world. Next lemma we're going to solve is, or prove is, mole power. And that is if we have A, B, N, all my naturals, then A times B to the power of N is equal to A to the power of N times B to the power of N. How are we going to do this? Well, we know how to deal with things of A to the power of successor or something, so I'm guessing we'll probably want to use induction on N. Induction N with 0 and successor N prime inductive hypothesis. Let's look at this case. A times B to the power of successor N prime. Okay, let's start by rewriting this in terms of power successor. That seems like a pretty good first step. A times B times A times B to the N prime. Okay, now we can apply our inductive hypothesis already. Let's see where that gets us. Okay, now we have, A times B times A to the N prime times B to the N prime. Okay. Here we could just move things around and combine them. Like, pretty much, this is just, if we distribute the parentheses correctly, we can get something we want. And I think we have a tactic simp, which uses lemma and hypothesis to simplify the main goal or target. Maybe you can do the simplification thing, but like, I think we want to get everything in terms of like parentheses. So let's apply power suck a few more times. Power successor. Okay. Now this is a thing, just like moving terms around and moving parentheses around. So I think we could maybe do simp, and then we could do it. We want to, from a multiplication world, mole commutative and mole associative. Mole associative? Does that get us something? A times B. Okay, did that do anything? Did something? Okay. Now we have A times B times. And also we want to use mole left commutative. I don't know. Oh, that worked. Okay, so pretty much it combined, like, Lean figured out itself what order of mole commutative, mole associative, and mole left commutative needed to be done, and like repeating them to get us to a place where it solves it. Oh, that's awesome. Okay, so pretty much we started with this whole mess, and I guess we could figure out the explicit things that are needed. Let's see. We want to. Yeah, I'm kind of curious what the explicit ones are, so I'm gonna try to do this one manually. I think we can do a. What's mole left commutative again? A to the N. Not quite that one just yet. Okay, we want to move the parentheses around. So we want to just swap these two. And for that, see mole commutative, mole associative. Probably mole associative first. Associative first. On what though? Because A times B times that. Now it's like this. Well, now we can do mole left commutative. No, not yet. Now we want to swap B in this, so mole commutative and B. Okay. Oops. Now A, B, A to the N, B to the N. Wait, did I guess what we wanted? Invalid field. Oops, not dot, comma. Yeah, nice. We have A to the N. Now we can like reverse mole associative, I think. Mole associative. No, that's not what we want. Now do we use mole left commutative? Nope. We just want to move the parentheses so they're mole associative. What does mole associative do again? That goes A times B times C to. Okay, yeah, we want to do this one on A to the power of N prime. Associative. Nice. Now we can do reverse mole associative. We're so close. Oh, is that it? Okay, now we want to swap B to the power of N times B. So mole commutative B. Are those equal now? Yes. Beautiful. Okay, I guess we didn't need to use mole left commutative, but I think I kind of like redid mole commutative maybe by some of this ordering. Mole associative. Is there commute associative commute again? Yeah, it's probably, yeah, I'm not sure why it didn't work simplify the first time, but here's a way to do it with just these two, and instead of having to do it manually, you can just have the simplify figure out things for you, and that's very nice. And then we have the sorry case. That should be easy. Well, we just turn everything into one. Okay, rewrite pow 0, pow 0, pow 0. I think that's also a repeat tactic. Is that repeat pow 0? Is that how we do that? Pow 0. Oh, what the heck? That's not right. Repeat Need rewrite power 0, maybe like this. Oh, okay, wait. I don't know why I have so many cases. And then can we just do rewrite mol1 ruffle? Not too sure how to use repeat. I'll figure it out later. I'll just use it the way I know. Rewrite pow 0, pow 0, pow 0, mol1 reflexive. And that's mol pow. Okay, pow pow. This is a power A, M, N, all my naturals. And we want to prove that A to the power of M to the power of N equals A to the power of M times N. So here we can see that power is not associative, because else it would not be M times N, it would be M to the power of N, but on the different side of parentheses. But as we know, exponentiation is not associative, so or commutative, so these are not true. So this is not true. And then let's figure out how to prove this. Okay, A to the power of M to the power of N. Probably something to do with induction here. On what though? I can see induction on A, induction on M, induction on N. I think N looks most promising because N's on the outside here. Induction N with 0. We'll do that later. In the case of successor N prime, the hypothesis. Okay, what are we dealing with here? We have A to the power of M to the power of successor N. Well, we can apply pow successor and our inductive hypothesis, and that gets us, what does that get us? A to the power of M times A to the power of M times N prime. We want to get that to A to the power of M times successor of N. So we want to combine these two. Is this pretty much, no, this is what we're trying to prove? Let's see, no. So we have A to the power of something times A to the power of something. We want to combine those somethings. What do we have for that? A to the power of something times A to the power of something. Bang. Okay, so I'm going to apply mol power in reverse, I think. Mol power. Or just regularly apply mol power. Wait, let's think about this. So for mol power, this one needs A times something times something to the power of something. And what do we have here? We have do we have A times N? No, we have, I think we want the reverse one. Okay, this one rewrite also failed. Why? So we want A to the power of N times b to the power of n. Well, that's what we have here. A to the power of something times b to the power of something. Okay, well, let's just... Oh, they need to be the same thing. N. So we need the thing that's being exponentiated to be the same thing. And I get a times b in the denominator. Well, that's hard. Pow add maybe? A to the power. Okay, pow add looks more promising. Pow add. Did that work? Yes, okay, nice. So it's a to the power of m plus m times the power of n. Great, we know how to deal with this. Oh, you just that's just like that's one of, yeah, that's just mole successor or something in reverse. Successor mole. Or mole successor. Okay, so is it a plus? Okay, is the plus at the beginning or at the end? Plus is at the beginning, so we want to use the plus at the beginning, right? Okay, so we want to use successor, mole successor in reverse. Oh, we need to put the parentheses around the right thing. Okay, so we need to have the parentheses around the a times b. So we want to use add associativity. Does that work? We need to use it in reverse, maybe. Oh, okay. Why did associativity not work? That's for 3 things. Okay, this is m plus m plus. Oops, too big. Let's drag it over. What's going on here? Okay, we're close to solving this. Pretty much, I want to apply mole successor or something. Oh, that works. Could I have applied mole successor in reverse already then? Was it the right way? Oops. Mole successor. Oh, I could have. Okay, I didn't need to do any associativity stuff, and that's just reflexive. And we're done. Oh, we have the sorry case. Sorry, we have. Okay, rewrite mole 0. Oh, back to this. Mole 0. Pow 0. Pow 0 and 1 equals 1 by reflection. Nice, that's power done. Now let's go on to the final boss of the power world. What I had a teaser for last time, that's add squared. We want to prove that for any 2 natural numbers, a, b, that a plus b to the power of 2 is equal to a squared plus b squared plus 2 times a times b. And how are we going to do that? Let's figure that out. Okay, that's nice binomial expansion. We might, okay. For this one that talks about something along the lines of 2 equals successor of 1, we have 1 equals successor of 0. Let's also add, I guess we put it in addition world. Lemma 2 equals successor of 1. 2 equals successor of 1 by reflexive. Nice. We might need to use that. So I'm guessing and there's some tips here on how we should try to do something like rewrite 2 equals successor of 1. I need to reload my window maybe. Did this do anything? We should be able to turn the 2 into successor of 1, which we know how to deal with. Yeah, that rewrites it everywhere. Okay. That's fine, and then we can also rewrite 1 equals successor of 0. Oh god, that is pretty ugly, but I guess that's what we have to deal with. And then we should do pow successor, pow successor, pow successor, pow successor. Can I keep doing pow successors? One's gotta stop working at some point. It's telling me, like, it says I should do it repeatedly, but okay, that's what it feels. So all these pow successors, and now we have this monstrosity. Okay, but I do see to the power of 0. So I guess I could just pow 0, mol 1, pow 0, mol 1, pow 0, mol 1. Where'd that get us? Okay. Oh! Yeah, that got us pretty far. So I have A plus B times A plus B, which is like what? Which is, I guess, what squaring means. And that's cool that we're able to get from A plus B squared to A plus B times A plus B. Now we have A times A plus B plus successor of 0 times A times B. Well, that is very promising. Now we want to probably distribute this multiplication. How do we distribute? Add mol. Okay, so we want to use add mol. Add mol is 2 things add multiply. Okay. Add mol. I have A times A. Okay, we're probably going to want to use add mol a couple times. Add mol. Just one was enough, I guess. Okay, add mol. Is there a mol add? Can we distribute A times this like that? Let's check. Add mol. Do we not have a mol add? No, we do have. Oh, we also have a mol add. Okay, add mol. Mol add. Mol add. Crikey. Okay. This is looking very promising. AA, AB, BA. Okay, well, we can turn BA into AB. So add commutative on BA. Oh, sorry, mol commutative. mole commutative on BA. Okay. Oh, so close. AA plus AB plus AB plus BB. Okay, let's just get the A's, AB's together. AA and BB in the front. We can we do add left, add right? Can you do, what does that give us? AA plus AB plus BB. Okay, now it can maybe add commutative on A times B. Okay, and now we want to like move our parentheses over. Add associative. Add associative. No, we want to do the reverse. Nice. Okay, very close. Now we have A times A plus B times B plus A times B plus A times B. And now we need to somehow turn that into successor of 0 times A plus B. How do we combine? How do we say two things add together if they're the same thing equals 2? Do you know the lemma for that? I guess we could add another lemma for that. Yeah, I'm not sure. Oh, it's so close. Let's look what we have in our multiplication world. We can swap things. We have times 1. We don't have times 2. We don't have adding 2 things. So we're probably going to want to introduce a new lemma. What are we going to want to do? Well, we're going to want a lemma. Probably want to put this in the multiplication world. So if we have mole 1, we're probably going to want to have a mole 2. Lemma mole 2. Or, I guess 2 mole. 2 mole m minat. Well, 2 times m is equal to m plus m. So we have 2 of the same things, they're equal. Can we do this reflexively? No. Okay, we can get a little more clever than that. I don't even know how we go about proving this though. M plus m. How to relate addition and subtraction. Mole add. Oh, I guess we could do 1 times A plus 1 times, like 1 times, yeah. That's, we can use mole add, so we'll only use mole add for this 2 mole. Pretty much the idea is we're going to turn m plus m into this, and then it'll go into, or we're going to have, what are we going to have? We're going to have m's be the t's, and a's be the 1's. Okay. So let's actually do it the other way. Let's m plus m. Let's call it, I don't know, add double m. Why? What is this? Add No, add same. I'll just call it add same. Equals. I guess I can also do successor of 1. Let's do 2 times m. Okay, that looks fine. How are we gonna do this? Well, we can change m to m plus 1, or n times 1. So let's do 1 mole. The first 1 mole succeeded, right? Oh, it didn't succeed? Wait. 1 mole. 1 mole on m. Why did you not work? Oh, wait. Too many 1 moles. Whatever. Okay, now we can do mole add. Huh? Oh, too many commas. Mole add. So we want, what is mole add? No, we want mole add in reverse. Mole add gets us 1 times m plus m. No. We don't want that. We want to add the 1s. Yeah, we have add mole. Okay, so at this point we have so we have 1 times m, 1 times m. We want to combine the 1s. Oh, so we want to use add mole, not mole add. Okay, let's move this down here. Heck yeah, okay. Now we have 1 plus 1. Now we should prove 1 plus 1 equals 2. I don't even know how to do this. This is actually a really hard book. I think like Principia Mathematica took like over 100 pages to prove this, so this might be a little tricky to do, but let's see what I can do. 1 plus 1 equals 2. Take this for granted, but we need to have a computer prove it. You need to like write down every little step. I guess we just apply like 1 equals successor 0, and then we combine the successor zeros with successor add. Successor of 0, and then we 0 add. Notice and successor of 0 is 1, so 1 equals successor of 0. But we want to do that in reverse. Okay, and then now we can also apply 2 equals successor 1. Nice, and then 1 mole and reflexive. Okay, now we have this proof add same, so let's use that in our long proof. Add same. I think we might need to reload our window if we change things in different files with VS Code, but let's see if this works. Fingers crossed. We don't need you to be that big. Okay, it's compiling and running the code. Did we have progress? Okay, add same. M plus M. Okay, so we want to add same on AB, AB. A times B, A times B. Okay, add same. A times B. No, get smaller. What went wrong here? Are more parentheses in the wrong place? That might be it. After add associative, what changed? A plus B. Well, I want parentheses around the last two A plus B, so how do we do that? Addition world. Okay, add associative. Okay. Nice, we want to apply add associative. And we want to apply add associative. Add associative to A times B. Did I find anything? Oh, is that associative three things? What? Add associative A plus B plus C. Oh. So we want to do add associative, not on A times B. We actually want to do it on B times B. Does that work? B times B, A times B, A times B. Did not find instance of expression. Huh? That's exactly what we have. Isn't it? Or is it? Okay, wait. What do we have here? Add associative A times A is first. No, that just undoes what we did here. We need to combine like have the parentheses around U as well. So we want A plus B plus C. What's that? How do we do that? Let's figure that out. Oh, it's so close. I can taste it. Let's just delete this, what we have here for now, before any of these add associatives. So this effectively, let me just copy this to see what we're working with. This effectively is parentheses around this. Okay, now I think we apply then a regular add associative. Add associative. Nice. Okay, now we can apply add associative. Nice. Add same. Let's go. Okay, now we need to apply add associatives in reverse. Add associative. Are we at a place to, oops. Okay. Huge, this is huge. Okay, now we want to, well, 1 equals successor of 0. Oh, in reverse. Two equals successor of one. One more mole associative. Let's do it the other way so it looks cleaner. Oh, and I think we're finally done. Wow, this proof was so long. We're out on column 338. 400 characters typed for this, or 300, over 300 characters typed for this one measly proof of a plus b squared equals a squared plus b squared. Well, I'm glad we have higher level tactics like simplify to make hopefully things like this easier, but I guess it was fun to write it out. I don't know if fun's the right word. It was interesting to write it out manually the first time around, but I'm very satisfied with this power world and that we're able to prove at squared. And similar techniques could prove all sorts of complicated identities of distribution, and so on and so forth, like binomial theorem, probably. That would be a cool thing of a plus b to the n and how that has that addition. But yeah, thank you so much for joining me on this journey. We did add squared, and that took quite a bit of time and quite a bit of effort, but we got there in the end. Yeah, if you learned something or enjoyed, please leave a like or a comment. Yeah, thanks for watching.